So now we can do inference for logistic regression. And the idea is the same as in a linear regression, which is that the data are random, right? So the coefficients that we're getting out, the kind of model fit that we're getting, depends on the data that we started with. And we would like to know how different things would have been if we had used a different random sample from the population. So as in linear regression, everything comes down to what the coefficients are, right? That totally determines what this function is that we're fitting, and we're gonna just try to quantify what is the sampling variability of these coefficients. So to do that, if we start by assuming that the conditional log odds, we'll talk more about that, are linear in x. Basically, we're assuming that this model is correct, right? That y given x is indeed Bernoulli. That's not an assumption. If y is binary, the only conditional distribution it could have is Bernoulli. The question is, what is the probability? How does the probability of y change with x? So the assumption is really that probability, that conditional probability, is following this logistic function wrapped around this linear function. So that's the assumption that we're making. If you do that, then there's some quote-unquote easy math that you can do. And you can show that, in fact, yes, this estimated coefficient, the set of estimated coefficients that you get if you run linear regression on a data set sampled from such a distribution, those coefficients, the sampling distribution is going to be normal. And moreover, the asymptotic variance of that coefficient is going to be given by some particular equation. And that equation is quite messy. But we call that the classical variance-covariance matrix for these coefficients. So very similar to linear regression. And you can do this in R. So I'll just show you right here. Copy paste this into R. It looks very similar to the case for linear regression. So if we load this data, run our logistic regression, we already did that. If you want to get the estimated covariance matrix, you can just use vcov. It's the same as with linear regression. And here, run that again. Okay, so here we're going to get this matrix out. So this is the variance, the estimated variance of the intercept coefficient. This is the estimated variance of the age coefficient, and this is the estimated variance of the this age group coefficient. And these are the estimated covariances between all of those because there's 3 coefficients. So they have a joint sampling distribution. So there's some covariances there, and those things are all estimated with this vcov function. And the math is not important to understand. If you want to then leverage that to build a confidence interval, you know all you need to do is take whatever the value of the intercept, the coefficient you got, and add plus or minus 2 times this, right? Same with the age coefficient. If you want, you just add plus or minus 2 times, 2 times the square root of this, because this is a variance and you need the standard error. So that also you don't need to do manually. There's this confident function that you can use, and that will build these confidence intervals on the coefficients. Now I'm showing you this, but I actually don't want you to ever do that, ever. And the reason is that, like for linear regression, where this easy math relied on this very crazy assumption, same thing here, right? Why should we assume, in order to estimate the variance of these things, that this is the true model, right? Like we could very well have a situation where the risk profile in our covariate is something like this. Okay, we can still fit linear regression and we can still get the best fitting sigmoid curve. But in order to understand what the sampling variability is, why should we limit ourselves to assuming that our data were generated from a model in this class? That doesn't really make much sense. So let's not make those assumptions. And can we do better? And yeah, it turns out it's perfectly easy to do that. Yeah, the math is a little bit harder. But since you're not the ones doing it, why should you care? Somebody else already implemented it. So there's no problem. And it turns out that, yeah, if you do this harder math, you just get a different equation. There's a different code that you need to write, but you can get this, what's called the robust variance covariance matrix. And again, just like linear regression, it's very easy to get this robust variance matrix. Instead of writing vcov, you just write vcov hc, and you have to use this sandwich package. That's where this function lives. And then if you want to get tests of these coefficients or confidence intervals, use this LM test library. There's other ways to do it. I mean, you could do it manually, right? Just subtract 2 plus, take a square root of the stuff in here and subtract and add 2 times that to the coefficient. And similarly for the tests, you can do it the way that we did it in week 8 or 7 or whatever, where you are manually computing the p-values by comparing the test statistic to a standard normal distribution and plugging all that stuff in. But R will do it for you, right? So let's try it out. So load these COVID testing data and use logistic regression to estimate the conditional probability of, so we already did this, positive COVID test given gender and age, and include an interaction, and then we want the coefficient on gender, but now we also want a 95% robust confidence interval and p-value, testing the hypothesis that the population coefficient is 0. So just gonna copy paste from here and go over here, and let's go back to where we were. We had this COVID testing data, do our logistic regression as desired. So let's just look at it. Great, seems good. And now this, load that. And there we go. So this is our table of the coefficients. We are interested in this one. So this is the estimate. Here's the robust standard error. And this is the p-value that's based on that robust standard error. So this is slightly different than what you would get if you used the VCOV instead of VCOV HC. And for confidence intervals, CoFCI works for that. So this generates the confidence interval, and we're interested in this one here. So this is what we've got.